Happy day, everyone. This is Orekoya Olusegun Physics Mathematics Fundamental on YouTube. Before we go into today's topic, please do not forget to subscribe, like, share, click on the notification button, and make a comment concerning this video. For partnership, these are the information, personal information, and then for partnership, the open account, everything is stated there. Now, today we want to solve a problem under ordinary differential equation. We have different methods of solution. Those methods, we have a separable variable method. We have what is called exact and non-exact method. And we also have what is called Bernoulli method, and so on and so forth. But today, we are going to solve a problem that involves the exact method of solution. But before we go into the solution, please, we need a background of calculus, differential calculus and integral calculus. If you need to do a refreshing work, please, it is advised that you do so that you can understand my presentation today to the solution. Now, we are given this particular problem, and we have discovered that the separable variable method cannot be used to solve this problem. So, there is a particular method that is called the exact method, and the exact method involves the application of a partial differentiation. Partial differentiation involves a particular dependent variable against two or more independent variables. Like for instance, let's say we have this particular function x, y. So if we want to differentiate, we can have the partial differentiation of this function with respect to this independent variable x, and we can also have partial differentiation of this function xy with respect to this particular independent variable y. So in this case now, we assume that x and y are independent variable with respect to function f. So that's where the idea of partial differentiation is. Now, for us to use what is called exact solution type, we need to do partial differentiation on each of these. Now, we need to do partial differentiation of this particular expression that we have here. That is delta 2x y squared minus 4. But because we are having this particular independent variable with respect to this independent variable, we are going to do it against this other variable. So we are going to section this into two parts. Now we do the same thing for this one now. Delta 2x squared y plus 3. Because we are having this particular variable, we are going to do it with respect to the other variable x. That's what we are going to do to test for the exact. Now, since we are doing with respect to variable y, that means variable x is assumed to be constant. So from our knowledge of differentiation, we use this power now to multiply. So we are going to have 4x. Then with this one now, 4xy. That's what we are having here. Now this constant, when we differentiate this constant, because it doesn't have y, it will be 0. So now let's test with respect to x here. Y is assumed to be a constant. So when we differentiate with respect to x, this constant plus 3 will be 0. That is in respect to our knowledge of differentiation. Differentiation of a constant will always give you 0. So this place will give you 0. So when we differentiate with respect to x, we use this power to multiply the coefficient of x here. So we are going to have 4xy. We can see that our results here are the same. So this means exact solution method can be employed. So in that case now, anytime we want to involve the exact solution method, we think about a particular function f, which is elements of a real number, such a way that elements x, y are also elements of a real number. Now, in this case now, what we are going to do is this. We are going to have something like this. That particular function, the f, is actually equivalent to what we have represented to this, the x. So we have 2xy squared minus 4 dx. So in a nutshell, if you want to get this particular function f, that means we need to differentiate the f. Please, this is the logic. Look at this. Normally when you are integrating as raised to power n dx, what we do is to add plus 1 to this power. Then whatever we have, we use it to divide. So we have as raised to power n plus 1 divided by the power that we got, n plus 1, then plus c for infinite integration. That's the idea. Now, so in order for us to get this particular function f we are looking for, we integrate both sides of the equation. So if you want to integrate something like integral dy, you see there is one that is here. So I can introduce variable y here, but in this case variable y will be y raised to power 0 dy. So to integrate this now, you add 1 to 0 plus 1, you can see all over 0 plus 1, then plus c, the constant of integration. So 1 plus 0 is 1. So 0 plus 1 is 1. So you have y over 1 plus c, which is same as y plus c. So in a nutshell, when you are integrating the f, using this idea that I put forward here, the f will give us f. So this one will be f integral 2xy squared minus 4 dx. So our differentiation, our integration is with respect to the x. So in a nutshell, we are going to y, in this case now, y is assumed to be a constant. So we are going to have 2s raised to power 2y squared minus, this will be 4x. So you divide this one with the power that we got after we had 1 to this power of x. So divided by 2 minus 4x. So if you look at this one now, these two cancel these two. So the f now, now before we move further, we are going to write this one, we say plus a function of y here. That's instead of putting the constant of integration c, we normally put another function of y. It's equal to this f, like this. So these two cancel these two. So we have f is equal to x squared minus 4x plus f function of y. Now, what do we do? If you go into this place now, this other side that we have here, we can say that the f here is equal to 2s squared y plus 3 dy. So, like what we have here now, the f dy. So that means the f over dy actually is equal to 2s squared y plus 3. So now, what we need to do is this. This particular expression that we have here is actually, you can write it as f prime of y. So that's that for this. Now, if you look at this place now, to be able to get f prime of y in what we have originally, we can differentiate what we have here. So this f prime, the derivative for this f prime, we differentiate. When we differentiate, use this to multiply. That will be 2x minus 4. We now say plus f prime of y. Now, if you look at this, what we have here, sorry, this particular y square, I didn't put it. So I have y square here. This particular y square is a constant. So I have this y square here. If you compare it now, we have this expression. If you compare these two expressions, they are similar. So you can say equivalent to 2s squared y plus 3. Now, this 2s squared, this is 4x. If you look at this one now, the what we have here now, we can see that when you when you compare this, what we have here will be equivalent to 3. So that means f prime of y is equal to 3. So in a nutshell, the solution, since we have gotten our f prime of y to be 3, we need to get f of y. That means we are going to integrate f prime of y, and it's going to be integral 3 dy. When you integrate f prime of y, it's going to give you f of y, and if you integrate this one, give you 3y. So we now put our 3y into this place. Sorry, this place is supposed to be 2xy squared minus 4x plus f prime of y. So since we have gotten our f of y that we have here to be 3y, the solution to this exact method is going to be x squared y squared minus 4x plus 3y. This 3y, we had the constant of integration to it, plus 3y plus c. So these are the solution steps to solving the exact method of ordinary differential equation. I believe that you must have learned one or two things in my presentation. I'm so happy having you, and I'll be happy having you next time. Have a nice day. Once more, this is Orekoya Olusegun, Physics Mathematics Fundamental on YouTube. Do not forget to like, share, subscribe. Click on the notification button and make your comment. Have a nice day. Bye.